Luc actually came to Aachen, for which I'm personally extremely grateful. Now, he didn't have a super long way just from Leuven, so not just across the border, a little bit further across the border, but still, it's wonderful to have him here. Luc is one of the world's leading experts on integrating learning and reasoning in AI. He is known internationally for his contributions to statistical relational learning and to probabilistic and inductive programming. And on topics related to that, in 2015, he landed an ERC Advanced Grant, which is one of the biggest and most prestigious European grants that you can get, as many of you know. He's a full professor at the Computer Science Department at KU Leuven in Belgium, where he also is director of the Leuven Institute for AI, so their AI center. In addition to this, he holds a Wallenberg guest professorship at Örebro University at the Center of Applied Autonomous Sensor Systems. He's very decorated for his scientific contributions, of which there are many. He's a fellow of the European AI Association and a fellow of the AAAI, and also a trustee of ICHCAI. So he contributes very, very significantly, not just scientifically, but also to running conferences worldwide. So he's very prominent there, and a very valued member of the international AI community. He's a founding member of the International Machine Learning Society and a laureate of the Royal Belgian Academy of Sciences. Luc actually has an interesting history. He spent a lot of time in Leuven. Apparently you like it there. That's great for Leuven. You did your PhD in 1991 there, I believe, on interactive concept learning. So you've been doing learning way before it became a universally acknowledged hot area. Good for you, good for all of us. And then you did a postdoc over also for the Belgian science organization, and then you began your professional career at Leuven. But he didn't like Leuven well enough that he said, let's just stay here forever. No, in fact, he went to Germany. He should have really come to Aachen, right? But that was maybe too close to him. So he went to Freiburg instead, very beautiful place. And you had a chair there as a full professor for machine learning and natural language processing at the Albert Ludwigs University for 7 years. So he was there, he learned German, he interacted with all the German things, including German university administration. He liked that very much, so much that after 7 years he went, now I can go and bring all this great stuff back with me to Leuven, right? And maybe not quite, but hopefully some good things and some good memories. Luc has co-authored 320 scientific works that attracted over 22,000 citations. So everybody knows Luc and his work. And he has co-advised and advised close to 30 PhD students and close to 20 postdocs, of whom 10 are now professors at universities around the world. So Luc has made a big impact, and yet he's not retired. He's very actively researching in this area that is really quite fascinating, that's trying to basically make learning better by injecting some reasoning and vice versa, which I think is a really, truly exciting research area. Before I give the floor to Luc, just a few housekeeping notes. I know this is the boring part, but then it gets interesting again as Luc takes the stage. So after this brief introduction, I didn't take 10 minutes, hopefully, didn't mean to. Of course, we're going to have Luc's talk, to which we very much look forward. Then we have some time for questions and answers, both from our lecture theater here, as well as from our audience online. And after that, and I'm very sorry that for those of you online, this won't work so well. Outside here, there will actually be an opportunity to stand together, talk with each other, talk with Luc, and have a few bites to eat, which is rather nice. So there are some advantages of being here in person. Good, so that's the plan for today. And the housekeeping notes are as follows. We will be taking photos, including, I believe, screenshots. So if you don't like that, maybe put something over your head, or I don't know. So we will do that. The talk will be available on our YouTube channel after the fact, but please don't go away. It's much more exciting to hear it live. Do subscribe to our newsletter on our webpage, the webpage of the RWTH AI Center, and do follow us on LinkedIn. So now that we're done with the advertisement block, it's my great pleasure to welcome Luc De Raedt.
Oh. Okay, thanks a lot for the very kind invitation and the very flattering words. It's great to be here. It's great to be able to talk about machine learning and machine reasoning. In the old days, I was always talking to the reasoning guys, you should do machine learning. Now it's the other way around. I'm talking to the machine learning people, you should do reasoning. And we've been trying to do that over the past couple of years with a lot of people, some of whom you find on the slide. If you're interested in the Leuven AI Center and have a look at what is there, I would recommend just type in Leuven AI in Google, and you'll see also a lot of activities from my colleagues and the kind of things we do over there. Okay, so learning and reasoning are both needed. I mean, it comes up in numerous different forms. I mean, Hector, he likes to talk about solvers and learners. Others like to talk about system 1 versus system 2. Some people talk about thinking fast, thinking slow. And so the book that you see here is very popular. It's used all over the place in AI. People think you really should combine the two approaches. Sometimes it's called like data-driven or knowledge-driven. And I guess everybody agrees that now is the time to really combine, to really integrate these two areas and get the power of both techniques. What people don't agree upon is like how to do it. There the opinions vary. I mean, people like Jan LeCun and Banjo, I mean, they say neural networks are going to solve everything. Others like Hector Geffner and, you know, other people like Marcus Darwish, Leuven would say, well, there's also a role for knowledge to play and you should kind of combine the two. It's also clear and apparent if you look at the problems we have to solve in real life. This is the kind of question you get at your driver's license. If you want to get your driver's license, and of course, if you want to solve these questions, there's like these two roles. First, you have to analyze the images and recognize where the different objects like the cars and the traffic signs and the pedestrians are. But then in order to answer this kind of questions, it doesn't make sense to train neural networks with billions of examples. If you have the rules of traffic, you should be able to kind of use them and incorporate them in this kind of setting. Kahneman talks about thinking fast, and that's really the kind of instantaneous recognition, the kind of instantaneous inferences that you make without having to think about it. And that's what neural networks are so good at. And they're amazing also in processing vast amounts of data. But what's often forgotten these days is that there's also like these other paradigms that are good at thinking slow, at solving tasks, at reasoning tasks, where there is this multi-steps that you have to go through before arriving at the conclusion, like planning a trip to Aachen, for instance, is one of these. And in this, there was like two other paradigms that have been dominant in AI, I would say logic and probability. And also their integration has been pretty well studied within fields like known as statistical AI, probabilistic programming, and there's also been combined with learning. I'm going to talk about integrating the three steps, logic, neural networks, and probability in order to get even the best of learning, but also the best of thinking fast and thinking slow, so to say. And that's also described in the book by Domingos on the master algorithm, where he talks about 5 tribes of machine learning and the ultimate quest for the ultimate machine learning algorithm. He describes 2 more paradigms like learning by analogy and also evolutionary computation. Neurosymbolic computation can be regarded as the endeavor to combine logic and neural networks. And what you see today is that the predominant paradigm is really to push the logic inside the neural networks and then assume that the neural network will solve everything. We are going to take a different approach, and that approach is going to be inspired from this other domain. These combinations of logic and probability have been studied for at least 20 years now, probably more 25 or 30 years. And there's a lot of insights in how to combine logic and probabilistic models, say probabilistic graphical models with traditional logic-based knowledge representation. And we'll see that a lot of the similar approaches and similar problems come back when you combine neural networks with symbolic methods. And we've outlined a kind of state-of-the-art survey along 7 dimensions about things that they share in common and about similar solutions that can apply. There's a short version of that in that paper and the long version on arXiv. I should stress neurosymbolic and symbols is used in many different perspectives. Some people like Yiyan Choi, for instance, I mean, for her, the words are the symbols, and that's not a perspective that I will take. For me, it requires a kind of knowledge representation framework. Okay, we're going to take a different perspective. And it's also the case if you integrate 2 different paradigms that you want to have the originals as a special case. Then and only then can you talk about a real integration. And that's kind of lost if you look at the predominant paradigms of pushing the logic inside the neural network and assuming that that will solve it all. And so we're gonna propagate a different approach, in particular in these 2 different systems, deep problog and deep Stocklog, where we're gonna show how you can build an interface between the 2, where you have bidirectional communication. Okay, the first key message was really the StarAI and Neurosymbolic AI. They share similar problems and they share similar solutions. There's a lot of arguments for that, but the key argument is this, that there is like 2 primary uses of logic, and there's 2 primary uses of graphical models and forms of graphical models that kind of coincide. And if you then go to neurosymbolic methods, you'll also see these 2 methods reappear in a sense. This is standard prologue, propositional logic, so to say. You have like facts in orange. These are things that are true, like burglary, earthquake, and so on. I presume this is familiar with everybody or almost everybody here. Yes. And then you have like rules, like the fact that Mary calls if she hears the alarm and if the alarm goes off. So this is like rules that you can kind of read. Once you have these rules, you can make inferences, you can build proofs to show, for instance, that Mary calls is true and is a logical consequence of that theory. And you see 2 proofs on the right-hand side. One via the rule that alarm is triggered by an earthquake, the other that it's triggered by a burglary. And that's a bit of a proof theoretic perspective. There's also a different perspective where you rather use the logic as a kind of constraints, and it's kind of connected to the set solving perspective. You can view the same kind of rules as logical constraints, and then you have possible walls that kind of satisfy or not satisfy these kind of constraints. And the possible world that's indicated on the right contains true facts. Everything that's not listed there is supposed to be false. It's a possible world, an interpretation, and that interpretation satisfies the theory on the left, and that's kind of a model theoretic perspective. Now, if we go to probabilistic graphical models, there's also like these 2 uses of similar kind of techniques. You have the directed and the undirected versions. On the left, you have the standard Bayesian networks introduced by Judea Pearl, which are very, very popular. And on the right, you have like the undirected versions, the Markov networks. And both of these have been upgraded towards this use of logic, so towards probabilistic logics, and you see like a probabilistic logic version of that Bayesian network on the left, and you see like one on the right as well. And so the same kind of principles reappear. In Markov logic, you have like logical statements, and they act as a kind of soft constraints on possible walls. In logic, if a model or a possible wall does not satisfy the theory, it's impossible. Here, it's not impossible, it just becomes much less likely. And then the weights that you see there are gonna give an effect of that. On the left hand, you see more the kind of program notation for Bayesian networks that you can also work with. Now, if you go to the next level, which is combining with neural networks, then you see that the very same kind of style as what we have here will come back. There is the style where the logic, in a sense, acts as a kind of program and will determine the structure of the neural network. And that's what you have on the left. And on the right, you have like these constraints that act as kind of soft constraints. And in Neurosymbolic, it's kind of quite popular to use logical constraints as a kind of regularizer of the neural network. So to punish the neural network if it doesn't satisfy these constraints. If you go back, I mean, this is probably the oldest Neurosymbolic AI system, going back almost 30 years to Towel and Chevlik. And what they did is they would start from this kind of logic-based rules. They would rewrite it a little bit from left to the middle. And in a sense, what they were then doing is build a kind of proof tree. I mean, it's an and or tree that you find here, but that kind of proof tree or and or tree would then be used to train the neural network. The inputs would be at the bottom, and the outputs would be the kind of thing what you want to predict would be at the top, so to say. Then they would do, once they have the and or tree, they would do things that neural network people do, which is like add a couple of hidden nodes, add much more connections, and just get training done. Then also, once the training was done, they were doing the kind of reverse exercise, which is very reminiscent of what people today do in explanatory AI or machine learning. They would try to reconstruct the rules from the neural network, in a sense, so to kind of build explanations for what the neural network was doing. And so that was very visionary, but it's kind of an illustration of the fact that, I mean, this kind of proof structure is kind of quite fundamental in this endeavor. You see now modern versions of this, for instance, by the Kuzelka group in Prague, which builds also proof trees, injects a bit of fuzzy logic, and kind of continues with that. One very nice system that I think is the neural tier improver, the NTP, where you can again write down this kind of logical rules. But the cool thing about the NTP is that the proofs that you get are not hard proofs, they become soft proofs. And the idea is that in logic, you need really to unify predicates like grandfather would match grandfather, but they use embeddings to match also grandfather with grandpa, and then to allow the kind of reasoning that you typically have. And that is kind of quite interesting. They were able to use it also for reasoning. In both of these cases, the logic is kind of encoded in the network, and after encoding it in the network, I mean, the means to reason logically is kind of lost. So that's the neural kind of program, very much like the probabilistic kind of program. On the right, you also have cool systems. One very foundational is from Guy van den Broek's group at UCLA, which is in a sense adding constraints as regularizer, and it's called a semantic loss. Here you've got a standard example of a multi-class classification problem. And you see that the outputs correspond to the three classes, 1, 2, and 3. And if you do multi-class classification, this would be kind of a result that you wouldn't like, because 2 classes score quite high and only one of them should fire. And so what they would do is like they would impose constraints like this one that says there should be exactly one class that gives as an answer yes. And then they would, in a sense, use that to punish the neural network, to regularize it if that constraint is not satisfied. And they would do so by computing the probability that the constraint is satisfied. Then they would turn that into a kind of loss function. Probability that the constraint is satisfied is indicated here. You can derive it from these numbers, and then they would turn that into a semantic loss function that would be used to kind of regularize the neural network. Semantic loss has nice properties, and it's also kind of a very basic foundational perspective on this kind of use of soft constraints or hard constraints in neural networks. You'll see it also in the work by Serafini and Gasset, where they use kind of logical expressions to encode it in these networks and to regularize You have SBR from the group around Diligenti and Gori in Siena, which is doing something similar. And again, you see that, I mean, the logic is in a sense used to punish or to regularize the neural networks. And afterwards, it's kind of gone. Once you do inferences, there's no more logic involved. The neural network is supposed to do everything. And I think that's disappointing. I basically propose a different approach where you can really mix the two. One thing that I'm going to skip is this. So I propose a different approach, which is really where you have an interface between the two. And interfaces are not pipelines. I think pipelines are for plumbers, and they go only in one direction, but an interface is really something that allows you to communicate from the neural network to the logic and backwards in a sense. And I'm going to illustrate that on two of our systems. The first is based on these probabilistic programs, and the other is based on...
We have a problem with the audio. Sorry about that.
Okay.
Let's quickly try Marco to fix this. So our online audience. Is it back? Yes. Great. Sorry about that. But let's just make
okay.
Sure
Good. Okay, so like in probabilistic modeling, okay, you have like this directed, this undirected, but you have also like two other classification which you can look at. If you have graphs, you can look at a random graph model where each edge is in or out with a particular probability, or you can look at random walks in the graphs. And this gives rise to also two of these probabilistic logics. You can also view it as the Bayesian network version versus the probabilistic grammar version. And both of these you can actually extend towards Neuro-Symbolic. And that's also a little bit our recipe in the past few years. Take one of these logics, probabilistic logics, and inject what we call neural predicates. The advantage of this approach is that if you work like that, you retain the full expressivity of the original frameworks. So you get the full expressivity of the probabilistic logics. You get also the nice semantics of that. And you can reason both logical, probabilistic, and you can use the neural networks, unlike some of the other systems where everything is pushed down into the neural networks. And in addition, a lot of fuzzy logic is used. So let me give you the perspective of going from this prolog to problog, and then adding neural networks. So this is the example that I was giving you. The burglary example, and then it's the seminal work of people like Sato and Poole in the 90s, who were looking at injecting probability in this, and they were looking for the simplest, non-trivial way of doing that. And in a sense, the basic concept of probability theory is a random variable. The basic concept in logic is a propositional variable, and so they kind of unify that. The additional insight that they had is that the only other thing that you need to do is to inject this probability into these facts. And so all of these facts become probabilistic. Now, burglary is true with a particular probability, and earthquake is true. And all these are kind of marginally independent of one another. It's a bit like the nodes in Bayesian networks that don't have any parents. They're also marginally independent of one another, and the dependencies are given by the structure of the Bayesian network. Here, the dependencies are given by the additional rules, so to say. So that's like the probabilistic programs, probabilistic logic programs. Once you have that, you of course need to define what it means. You have to define the probability of queries that follow that from conditional queries. Here, we indicate how to compute the probability of alarm. There's two proofs, and the probability of every proof is just the product of the probabilities of the fact that you encounter in that proof. And then it's kind of tempting to just add the probability of these two proofs to simply get the probability of alarm. But that is, of course, not allowed because, as we all know, the laws of probability say that if you have the union of two events, you should also subtract the intersection. And that is actually the thing that is called the disjoint sum problem, and that is actually leading to a lot of computational problems. It's this what makes it kind of intractable and sharply complete probabilistic inference for that. You can also view these programs as kind of generative processes. Here you've got this kind of generative tree. At the top, you have the empty walls. Then earthquake is true with 100%. So in the top, in the other top node, earthquake is there. If earthquake is true, you can add alarm. Then you go left. So here we got earthquake and alarm, and you can kind of descend. And at the leaves, you'll get the possible walls together with their probability. And then you can also indicate what's the probability of alarm. It's the probability of all the walls in which alarm occurs. And that's the orange ones that you get. It's clear that you can represent what Bayesian networks can represent. I mean, all what you have to do is look at a CPT, I mean, the conditional probability tables of the nodes and map them onto kind of rules. And in addition to that, you get also the power of a programming language. So it's Turing equivalent. So you get a lot of expressive power with these probabilistic logics. Also probabilistic databases, you get as special cases of this. Why are people interested in doing that? One of the reasons why StarAI is been investigating that is really that you want to reason over multiple, you want to reason at an abstract level, for instance, over students, over courses, and this kind of plate notation is one illustration of that. It ties together multiple students, and as you see here, this kind of plate notation, if you add some students, well, and courses, you basically get this unrolled network that ties everything together. And you can reason at the abstract level. With the probabilistic logics, you can add ontological knowledge, you can compute, you can do a lot more. There's applications that we've studied in like game playing, to build models of the opponent, to see how things evolve over time. We've done things in robotics to reason about occluded objects, for instance. What's quite interesting in robotics is that we've also done things like learning the effects of actions, the kind of probabilistic strips operations where there was a babbling phase where you first learn what the effects of your actions are. Like if you tap certain objects with certain forces, how far will it go? And we've done that also with kind of continuous variables and on real robots. So there's a lot of extensions of these probabilistic logics. One that I want to mention here is one that we've been developing over 10 years now, is really injecting also like continuous distributions, like for instance, being able to express that the length of something is distributed according to a Gaussian, and then adapting the logic and the inference to work with that. And it's these versions that we've used in the robotics applications. Biology, we have stuff. If people are interested in this, I would say just visit the website, search for Problog, and you'll find it. But I should talk about Neurosymbolic, and going to extend it, these probabilistic logics with neural networks. And when we started thinking and brainstorming about it, we were looking for something that would be as simple as the idea of Sato and Pool, really looking for basic concepts to kind of map from one to another. And we came up with the notion of a neural predicate, because neural networks, they are kind of functions, and they produce outputs for given inputs. For instance, for MNIST images, it would produce numbers between 0 and 9 with particular probabilities. And so what we did is kind of introduce this notion of a neural predicate. Here you see a neural predicate called digit. It will accept one of these images, and it will produce one of the outputs, namely 0 to 9. And the meaning of this internally is that it's kind of viewed inside the probabilistic logic as a kind of what we call this ADs, it will actually say that, you know, it will for each of the possible outcomes, it will assign a probability. Here, the probability that it's, for instance, the 7 will be 53, the probability it's 1 will be 35, and so the sum of the probabilities is, of course, equal to 1. And that's, again, all that you need to do to add that to your logic. Here you see, again, the very same neural predicate that we have, and you can then start using it. We use it in this addition example. On the right, you see 3 examples of training data, 2 MNIST images together with their results, and that's the only training data that it's given. It's given no training data at the level of the neural predicate digit directly. It's at a higher level. And then what you get is, if you fill out, you know, one of these examples in this rule, the rule starts to act as a constraint. And that's nice, because if you fill out this addition 3,5a, you know that 3 must map to a number and 1, 5 must map to another number, and you also know that the sum must map to 8 in a sense. And so a lot of possibilities are still possible. 4, 4, 3, 5, 2, 6 are possible, but 5, 5 and 6, 3 are impossible, because their sum is not equal to the 8 that is given. Okay, and then it's no surprise that with this knowledge, okay, if you compare to standard CNNs, that of course you do better. It's also not that much of an achievement. I mean, this is a very simple example, but if you change it slightly, that you work with sequences of numbers like this, the only thing that you need to change is like the definition of the knowledge that you have. You have knowledge about how to add numbers. The knowledge that you don't have is how to classify these images. And so if you give that to the DPROBLOG system, and you can also see that there you can learn. You also get the probabilistic version as a special case. And here is again a tiny conceptual example of doing that. This is a noisy version of this edition, that with a particular probability noisy, you'll generate a random number. And with 1 minus noisy, you generate the right number as before. And you can see that this DPROBLOG system is not only able to learn in these cases, but it's also able to recover the amount of noise in the style of the probabilistic variable. I'll be very brief about inference. Let it suffice me to say that, okay, what you do is you ground out your program. You get this kind of logical statements that you compile using knowledge compilation technology, you know, the kind of BDDs, DDNNFs, SDDs that are very popular. I mean, BDDs are these binary decision diagrams. You can map it then onto this, this kind of structure. And once you have these structures, what you do is you replace and by multiplication and or by addition, and you're into business, essentially. And that solves this disjoint sum problem that I was talking about. What's also cool is that to inject now neural networks, it was also quite easy. The only thing that we had to do is use the PROBLOG machinery to build these circuits. And then at the end of the day, what you get is that these neural predicates, they become the leaves of these circuits. And so you can put the neural networks, in a sense, down there. And then the examples are at the top. So you get the examples for addition at the top. And so you backpropagate the error from the addition to the neural predicates down into the weights of these neural networks, and you're able to learn, in a sense. So that is something you can do here. We've done a lot of other experiments comparing with state-of-the-art on like program synthesis a little bit. We've done a bit of word algebra problems before ChatGPT was solving these all. A bit on poker. We've simulated the neural tier improver. And that's kind of a quite interesting thing, because what it does is actually, it's kind of softly unifying, I mean, two elements like this grandpa and grandfather of. it's actually unifying that by matching it in a kind of embedding space. And also that you can simulate inside these logics. And you can then start to reasoning with these embeddings, you can actually recover embeddings in certain ways, but that bit as an aside. Let me also briefly go, because I think time is running out. I'm fine. Okay, we're good. To talk about the other logic, which is a bit more recent and which is much more efficient, and which is actually taking this kind of recipe. If you start from a logic, certainly if you start from a probabilistic or a fuzzy logic, and you want to inject neural networks, then you can use this concept of this neural predicates and build your, so to say, own systems. And one where we have done that is this deep stock log, which is using this alternative semantics for logic programs. It's stochastic logic programs, which are inspired on probabilistic grammars. And let me show that. Sorry for the switch of color. This is my students who likes black, and I was too lazy, I must admit, to kind of map it to white. So, okay, this is a context-free grammar. I guess everybody knows that. It recognizes numbers. Well, it recognizes expressions with numbers. You have like rules like an expression rewrites to a number, or it rewrites to an expression plus another number. And then you have like the terminals, the yellow symbols. And so that's like standard context-free grammars, and you get parse trees. Probabilistic context-free grammars are the next step. And what you there have is that the rules become annotated with, again, probability labels. It is the case that the sum of the probabilities for one non-terminal symbol is always equal to 1. Like for expression, there's 0.5, 0.5. For plus, it's 1. And for the numbers, there's 10 of them, so it's 0.10 in a sense, right? So you see that the sum of these is always equal to 1. And with this, you can then produce parse trees. And what you can also do is you can assign probabilities to parse trees. The probability of this parse tree is just the product of all the rules that you have applied in your parse tree. And if you apply a rule more than once, like you see the ones for E applied more than once, then you also multiply more than once in a sense, right? So you see the rules, there's only 2 rules for E, but still there are 3.5s in the product. And that's kind of quite interesting to, I mean, this probability is quite interesting to look at the most likely parse tree. People have taken also another direction of generalizing these context-free grammars, and they've looked at unification-based grammars. These were popular in the old days of Prolog and natural language processing. Essentially, what you do is these non-terminals, they get arguments. They can be variables. And this is kind of useful to reason, for instance, about number agreement between a subject and a verb, because it allows you to write down very compactly these rules. And it will also make that certain derivations, certain parse trees fail in a sense. But that's essentially what there is. And like if you look at these expressions, it can easily be used to compute the value to which this expression should be evaluated. In this case, 2 plus 3 plus 8 is 13. And you can kind of combine that with a bit of computation as is indicated there. If you have unification-based grammars as one extension, probabilistic as another, it's kind of tempting to merge the two. And this is what is called stochastic definite clause grammars. And that's also the basis of this framework for stochastic logic programs. And here you've got the benefit of the two. You can, in a sense, parse these expressions. And at the same time, you can look at what's the most likely parse tree. And for that most likely parse tree, you can compute the outcome as such. And it's this formalism that we now have extended with a very similar concept, injecting neural predicates. Instead of using these symbolic terminals, you can now use images as terminals. And you see it here, for instance, that for this kind of expression, you can just use the same kind of notation almost as for the problem. You can inject that, and you can also train then that for this sequence, you actually should get a 13. And again, the grammar will act as a kind of constraint to evaluate the right kind of parse trees. Inference. Okay, these parse trees, they were kind of proofs, if you like, certainly if you come from a logic programming perspective, because this definite clause grammars, can be executed in standard Prolog. So you get a kind of proof trees. And for this kind of proof trees, well, you get the structures that is indicated here. This mirrors, in a sense, the proof tree of the of miracles that I showed at the beginning. But what's more important is that on these proof trees directly, you can actually get circuits and apply the same trick as we did before. That is, you get the examples at the top, and then you push down the gradients down in there, and you get the learning. The nice thing about this is that because of the different semantics, you don't suffer from this sharply completeness of the grammar of the inference. I mean, if you look at context-free grammars and probabilistic context-free grammars, inference is polynomial. There is this famous CKY or CYK algorithm that is cubic. And yeah, that kind of efficiency is something that is very handy and that you get here. The kind of things you can do with this framework is still different than what with the other because of the different semantics, but still you can do quite a number of things. Certainly, if you try to use some dynamic programming, I mean, the kind of optimizations that you also have in this grammatical inference ones. It's much, much faster than the others, well, some of the alternative systems. And it can actually process longer length sequences. Like there was a system called NGS, which was quite specific for this kind of well, sequences, handwritten sequences, and that, yeah, you can easily beat with this kind of system. It's a lot faster as well. You can do grammatical inference, like for instance, recognize this context-free grammar with the parentheses. You can also do even some context-sensitive ones, like A to the power n, B to the power n, C to the power n. You can also learn this kind of things in a sense. And yeah, it's also, because of the connection to this Prolog, it's also a programming language still. And you can do some computation between this brackets, curly brackets, I think they're called. And so you can also like do some there, like for instance on link prediction with reasonable results. It's still preliminary, but it looks like something quite interesting. And well, I'm asking my students to look more at this model than at the previous model right now. Okay, let me conclude by some challenges for Neurosymbolic. There is some challenges in scaling up some of the models. We don't have enough experience with some of the others yet to say much. I think in real-life applications, we could do better. On Monday, there was a pretty interesting talk on Taylor from Véronique Ventos from Nuke AI, a French company that was having this competition last year with Bridge. And actually, there were 8 Bridge champions that lost against their system. And the key to the success is really that there's probabilistic logics and neural networks in there, because it can also provide explanations, the kind of explanations that Bridge players would like to get, in a sense, at a reasonable abstract level. And that's because they built in knowledge, they built in constraints, they're really using the power of this kind of logics. And so that's quite fashionable. I myself dream of the robotics applications. I mean, I was showing some, but this was like pipelines. And as I said, pipelines, I don't like them because you first train the neural networks, then you try to couple it to the probabilistic logics. I think it should go end to end. And that's like, in a sense, the dream to be able to train these models end to end and then cope. I mean, we now have also version that works with continuous distributions, with multivariate distributions of this deep problem and so on. Okay, let me conclude. I hope I've given some arguments that these two domains, probabilistic logics and neurosymbolic systems, that they share quite some problems and that also similar solutions do apply. And then I've also argued in favor of this kind of, well, other type of approach, not reducing one representation to the other and getting rid of it, but rather being able to use both of them at the same time. So thanks.
Excellent. So now it turns out that our Q&A will not be recorded. So don't be afraid if you ask a question that you're not so sure about, that it will be out there forever. It won't. Marco will turn off the recording right now.